Welcome back, everybody. This is the beginning of week number 6, so we're getting close to the wire here. You may have seen already, I moved the exam, the next one, and I gave you a little more time. It opens up on Friday at 7 a.m. and then it closes on Saturday. So you got all day Friday and literally all day Saturday to pick from, so you can go in there and do the exam. And I also moved the exam number 5. So this is week 6. The plan here is to finish chapters 10, 11, and 12. 11 and 12 are very short. 10 is a little bit longer. We'll finish that today. And then Thursday, finish up 11 and 12 and get you ready for the next exam. And then basically from there, it's the other 13, 14, 15, and 16 are relatively short. We'll probably have a couple of sessions at the end. They're basically going to be open for review. We'll see how it goes. That's generally what happens. The way doing lecture during exam day, that allows us to get a little bit early toward the end. It allows us to give you, I call it study day, so you can come in and just with any questions, I'll be here for the time, and you can ask anything you want concerning whatever chapter you want to talk about. There is, on the course website, there is a practice final exam PDF file. If you haven't downloaded, that's a good resource for you to kind of get you ready for the final exam, which again, online also is comprehensive. Okay. Chapter 16, you won't have on the test. That's the last chapter in gases, but you will have homework on that, but it won't be on the test. Generally, because by the time we get done with it, you don't really have enough time to prepare for it. So I will present it simply because it's one of the requirements of Maricopa to talk about gases and chemistry. It's fairly short chapter, and just the homework will be necessary. All right. What we got here? All right. Any questions? It's time to learn. Okay, there you go. All right, so let's jump into chapter 10. Chapter 10 deals with chemical reactions. Now, I mentioned this before in that of all the chemistry involved with respect to chemical reactions, there's only 6 types of chemical reactions. We talked about one of them, which was the acid and the base reaction called neutralization. Another one that you may be familiar with, or you should be familiar with, especially this past weekend, if we're out barbecuing with gas. You were barbecuing, you're burning propane. That's a combustion reaction. Combustion and oxygen. So we'll talk about all of them and have a little table to show you how to look at the reactions and how to be able to determine what type of reaction you have. Now, with respect to these reactions, we talked about the solubility rules. One set of these type of reactions require the solubility rules. Also on the periodic table, right above the solubility rules, there is another small table called activity series. We're going to be using that also to determine the type of reactions. Okay, so, but before we do that, we're going to talk as something we talked about before, the conservation of matter and energy. First of all, matter is not created or destroyed. We basically just move things around and create a compound from one form and just move it into a different form. Okay, now because of this, what this tells us is the total mass of, let me see here. the total mass of reactants. And so let's say I have a general reaction of A plus B to give us equal reacts to give us C. What that's telling us is that if I start off with 10 grams of A and B, maybe 5 grams of A, 5 grams of B, that when the reaction's complete, I should end up with a total of 10 grams, okay? That's a conservation method. If we were in person, I have an experiment here, that a demonstration you can even try at home. And it basically is a container with vinegar and a balloon. And in the balloon, I would put baking soda, sodium bicarbonate, okay? Now, then I would take a little bit of vinegar, put it inside the container, and then in the balloon, put the baking powder, okay? And something similar to this, you might try this. Let me draw this. So I would have a container, okay, with a little vinegar in there. And then I will have a balloon that, here's supposed to represent my balloon, that it would contain some sodium bicarb. So sodium bicarb or baking soda, and this is acetic acid, AKA vinegar. Okay. And then I will weigh that whole thing, okay, and get a total weight. And let's assume that this was, 50 grams, the total weight of everything. Then I would take the balloon and I would move it up and drop out that baking soda into the container. A reaction occurs, specifically a neutralization reaction. Baking soda reacting with vinegar, okay, reacts, and we get carbon dioxide. And what happens, that balloon starts to fill up. Still has some liquid, but that balloon starts to fill up with the carbon dioxide that's collected, okay, up in here. And after the reaction is done, that's noted by the fizzing action, we keep it on the balance and we weigh it. And guess what? We still have 50 grams of material. It's going to vary a little bit simply because that balloon is not 100% sealed. And so you might lose, maybe you might get like 49.5 or so, simply because that's in a totally sealed system. But it was a demonstration that here we have sodium bicarb, solid material, baking soda, we all know it's solid material. Here we have vinegar, acetic acid. This is one of the covalent acids, organic acids. They react to form carbonic acid, which breaks down to give us carbon dioxide and water. That carbon dioxide is a gas, goes into the balloon, fills that balloon up, and the total weight now is still 50 grams, okay? And like I said, if we were, meeting live, I could do that, but I don't have the equipment or the material to do that. That's a simple demonstration of a conservation of matter, okay? All right, so the fact that we have a total mass must equal, the total mass of products must equal the total mass of reactants. It also states that if, for example, I start off with X number of carbon atoms, whatever form they may be. In here, they're saying 254 carbon atoms, that at the end of the reaction, I will have 254 carbon atoms. They'll be in different forms, but it'd still be carbon, okay? Still carbon, still 6 protons, but in that example was sodium bicarb, it could be carbon in the form of solid material, or it could be carbon in the form of carbon dioxide gas. All right, so because of this conservation matter, we must what we call balance the reaction. When we write reactants and products, we have to write numbers, put coefficients in front of the formulas to tell us to balance. So if I start off with 2 nitrogens as reactants, somewhere in my products, I must end up with 2 nitrogens, okay? These coefficients are important because once we balance the chemical reaction properly, we're going to use those coefficients, which, by the way, ends up as another ratio. Remember way back when I talked about ratios, how you can write those ratios 1 or 2 ways, okay? And those ratios are important because we will use those ratios to do calculations in these chemical reactions. All right, so some of the types of chemical reactions that for you to balance them, it really amounts to a trial and error. It's a real trial and error. However, not all of them. Some of these reactions that we are going to introduce you to, when we balance them, there is a systematic way you can approach to balance the equations. But the others are basically, okay, let's try 2 units, a coefficient of 2, and then go over back to products and reactants. You go back and forth until you got the right coefficient. The thing to remember is when you finally do the numbers, the coefficients, make sure that the coefficients you utilize have been are the lowest terms, if you will, the lowest numbers that you can put in. Yes, you can balance them. If you balance a chemical equation, I can double all the numbers, okay? But what you want to do is if you use double the numbers, check and see to make sure that they're not divisible by some number that you utilize to bring it back down to those lowest values. I'll give an example of that here in a bit. Now, we don't use half numbers. All of these coefficients will be integers, okay? No half numbers. So we're excuse me, beginning, we talked about the periodic table. We talked about these elements that we can predict what type of charge oxidation number they have, be it positive or be it negative, okay? Then we start putting these together, the positive and negative, especially with ionic compounds, in the right ratio, okay? So now we've created compounds and we put in subscripts if necessary to make sure we have sufficient atoms of each to balance out the charge that they have. Okay, so now we went from the elements to compounds. And now we're putting compounds together to react with each other to give us products. Okay, all right. And so we're kind of trying to bring everything together here for you. And so that's what the first part is. We write the chemical formulas of the reactions. You may be given, it might be written in words, for example, sodium metal reacts with chlorine gas to give you sodium chloride. Taking that verbiage, if you will, the words, and then converting them into a chemical reaction is what one of the things we'll be doing. Once we do that, then we balance it by adding coefficients to make sure we have sufficient atoms, sufficient atoms of whichever atoms we're working with. All right, for example, if you look at this reaction, this could be worded as hydrogen gas in the presence of oxygen gives water, reacts to give water, okay? So keywords, hydrogen gas. We know that hydrogen gas, the term hydrogen gas means H, but the term gas means it's a diatomic. They didn't say hydrogen atom. They said hydrogen gas. That's important, okay? Because we know there's only 7 diatomic atoms, 7 elements that are diatomic, have no fear of ice cold beverage, right? So hydrogen is one of, oxygen is another one. So here, hydrogen gas in the presence of oxygen gas reacts to give you water, H2O. And so then we have to balance it. Well, what do I mean by balancing it? If you look at the coefficient, we see a 2 here, okay? That means we have 2 hydrogen molecules. So that's a total of 4 hydrogens, right? 4 hydrogens total. Then we have, there's a 1. When there's no coefficient, it's assumed to be a 1 there, right? And so we have 2 oxygens total. And then we look at the water. Water, with the coefficient in front of H2O says we have 2 molecules of H2O. That means that there are 4 hydrogens and total and 2 oxygens total. And guess what? We're balanced. Mother Nature's happy. We got 4 hydrogens as a reactant and 4 hydrogens as a product. We have 2 oxygens as reactants and 2 oxygens as products. Therefore, we are balanced. Okay. Now, furthermore, that coefficient in front says that I have a ratio between hydrogen and oxygen that I can write with hydrogen in the numerator or oxygen in the denominator, vice versa. Okay, that's that ratio between here and here, between these two. That's a stoichiometric relationship. We're going to have a chapter on that. This is the introduction to it. They're just telling me how many of each elements I need to react to form the product, specifically 2 molecules of water. All right. So that means I got a ratio between reactants. I also have a ratio between the reactant and the product, which means here I have 2 hydrogens over 2 waters, or written as 2 waters over 2 hydrogens. Okay. I also have a relationship between oxygen and water, which is 1 oxygen over 2 waters, or 2 H2Os over 1 oxygen. I have a total of 6 ratios here that I can utilize for calculations down the road. Okay, we're going to talk about the term moles, M-O-L-E, which is very crucial. That says here, that tells me that I have 2 moles of hydrogen reacting with 1 mole of oxygen, or 2 moles of hydrogen will give me 2 moles of water, or 1 mole of oxygen will give me 2 moles of water. That's that relationship that we're going to be utilizing, because down the road, you could be asked a question. Let me clear this up a little bit, like this. If I have 2 grams of hydrogen, how many grams of water would I create? Or if I have 50 grams of oxygen, how many grams of hydrogen do I need? Or I could be asked, I need to make 50 grams of water. How many grams of hydrogen do I need to make 50 grams of water? And you know, the interesting aspect about this relationship and this balanced chemical equation, that it is true whether I work with a quantity in the lab, okay, where I'm making small amounts, or I could be in some industrial company making tons of material. And that relationship, that stoichiometric relationship, is true, regardless of the magnitude of size. And these models here kind of represent what I just talked about. You can see I got 2 molecules of hydrogen, designated by the gray. The hydrogens are designated by the gray color, and the oxygens are designated by the oxygen. Okay, reaction proceeds. Okay, we create water, 2 molecules of water. Okay, so now oxygen has been converted from elemental oxygen to now a compound, a molecule of water, H2O. All right. This, by the way, FYI, we call a combination reaction. Generally, that means when we take 2 elements and break them together to form a compound. Did we not take 2 elements, hydrogen, oxygen, and created a compound, H2O? Okay, you'll see it here when we talk about the reactions. All right, so let's try to balance a few reactions. Here we have, it could be written out and say nitrogen gas in the presence of hydrogen gas reacts to form ammonia, NH3, okay? They're all in the gas phase. All right, so now the question here is to balance it. So we look at this. We got 2 nitrogens on the left, so we do a little grocery list, if you will. We got 2 to begin with. We got 2 nitrogens and 2 hydrogens and the reactant side. And now we got 1 nitrogen and 3 hydrogens in the product side. So you can see that we're not balanced. Our hydrogens are not balanced, our nitrogens are not balanced. Now, you can do this one any multiple ways. One way or the other is not totally correct. Okay, it's not correct. Whatever works for you. Now, one way is to look at the nitrogens. You can see that nitrogen, there's 2 nitrogens on the reactant side, but only 1. Now, we can, what if we put a 2 in front of ammonia? Okay, what does that do now? So that's initial. And so now we still have 2 nitrogens, okay? We still have 2 hydrogens, but now we have 2 nitrogens and 6 hydrogens, okay? 6. So now the nitrogens are balanced, but the hydrogens are not. So now we can go back to the hydrogens and say, all right, what if we put a 3 in front of hydrogens? Because that will give us 6 hydrogens. And we go back and double check. That's our third analysis here. So now we go 2 nitrogens as a reactant. We got 6 hydrogens now. We still have 2 nitrogens. And finally, we got 6 hydrogens. And guess what? Mother Nature's happy. We are balanced. And that's what balancing does. So you generally start either on the reactant side or the product side. You add a number and you go back and forth until you are balanced. We double check. Those are the lowest terms, the lowest numbers that we can have. I can't divide by either 3 or 2 to get a whole number. If I divide by 3, I get fractions, or divide by 2, I still get fractions. So those are my lowest terms. Now here I started with putting a 2 in front of nitrogen, but you know I could have gone with the hydrogens. I could have said, okay, I got 3 hydrogens over here. I got 2 hydrogens over here. We get a disparity. Find a common number, right? Like adding those fractions with, you know, 1/3 plus 1/4, right? A common number for the 2 and the 3 is a 6, right? So I can put a 3 here and a 2 there, and I got my hydrogens balanced, and guess what? It automatically balances my nitrogens, okay? So one way to attack it, one way over the other is not, one's not more correct than the other, doesn't make a difference. Bottom line is get to a balanced chemical reaction. Okay, so you got a 2 there and a 3 there, and we're balanced. Now what this says is once you balance it and you checked it, then be aware of the ratios between the reactants and the product. Between the nitrogen and the hydrogen, it's a 1-to-3 ratio, okay? 1-to-3 ratio. Remember, this is a 1 here, so I got a 1-to-3 ratio here, 1-to-3. And then from nitrogen to ammonia, guess what? I got a 1-to-2 ratio. And then from the hydrogen to the ammonia, I got a 3-to-2 ratio, or 2-to-3, whichever way you want to write that ratio, 3 or 2. So I got, again, a ratio. Not only that, notice that 2 elements, 1 new compound, combination reaction. Combination reaction, RXN meaning reaction, where I combine 2 elements to form a compound. Okay, we do the same thing here, very similar, whichever way you want to start. We can say, all right, let's go put a 2 in front of HBr. All right. Now this HBr would be hydrogen bromide. If it was aqueous, it would be hydrobromic acid. Okay. So if I put a 2 in front of the HBr, that balances my bromines, right? Because I got 2 as a reactant, 2 as a product now. And guess what? My hydrogens get balanced because I got 2 hydrogen in the form of gas, 2 in the form of HBr. And so I'm balanced. And so now my ratios are 1 to 1 for hydrogen to bromine, 1 to 2 for hydrogen gas to hydrogen bromide. Okay. Carbon monoxide in the presence of oxygen gives us carbon dioxide. This is one way to get rid of poisonous carbon monoxide, is to react it further with oxygen. All right, so if we put a 2 in front of carbon dioxide, that gives me 4 oxygens and 2 carbons. Well, that means I need to put a 2 in front of carbon, okay? So that gives me 2 carbons on both product and reactant. My carbons are balanced. Now check the oxygens. I got 2 carbons in the form of carbon monoxide and 2 carbons in the form of carbon monoxide, 2 oxygens in the form of carbon monoxide, and 2 oxygens in the form of oxygen. So my oxygens are balanced, my carbons are balanced. Note the ratio, 2 to 1 for carbon monoxide and oxygen, 2 to 2 for carbon monoxide and carbon dioxide. All right, so some of these reactions, again, are basically trial and error. Try this number, look at, analyze what you have, add a number to it to kind of balance and go back and forth to product, reactant, reactant to product until such time that you have a balanced chemical reaction. Then at the end, make sure you are down to the lowest terms with respect to the coefficient, okay? What I mean by that is this. You could balance this thing, and if I double everything, I could end up with 2, 2, and 4, okay? Which by all rights is balanced. It's a balanced chemical reaction. However, you don't have it down to the lowest terms because everything up here is divisible by 2. And so I can divide everything by 2 to give me 1, 1, 2, okay? All right, so writing reactions from words is basically what I just stated earlier. You might be given a paragraph or 2 or a sentence or 2 describing a reaction. So we want to break that words down and create the chemicals that they're talking about. And then don't forget the physical states, solid, liquid if they tell you, or gas. Okay, so that goes back, if you're dealing with the elements, goes back to that table that shows you who's the solids, who's the liquids. Remember, there's only 2 liquids of the 118 elements. There's 2 liquids and 12 gases, and the rest are solids. All right, and those are the physical states to refresh your memory. In parentheses, lowercase letters S, L, and G for solid, liquid, gas, respectively. And if these words tell you it's a water solution, aqueous solution, then we use the AQ. All right, remember which ones are solid, liquid, and gas, and remember which ones are diatomic, which elements are diatomic. There's only 7, 118 elements, and there's only 7 that are diatomic. Have no fear of ice cold beverage. Okay. Now we know about the subscripts. Subscripts tells us how many atoms are available. Oh, I got a phone call I got to answer. One moment, please. Okay, sorry, I needed to answer that. Okay, so remember your physical states. Okay, remember how we put the atoms together with the subscripts, and we have to put them together such that we end up with a zero charge. At least for the ionic compounds. With respect to the covalent compounds, you'll be given, a name, a formula, and then based on the formula, you can create the formula that based on what you're given, and the formula, you can write the structure. Okay, we did some of those before where we did carbon dioxide, for example, one carbon, two oxygens. All right, and the coefficient, as I talked about, that tells us how many of those molecules we need. You can change, once you set the subscripts, those are set, okay? Those are not removable. They're set, we don't change that. What we do change as needed is the coefficient. That's the integer in front of the compound. Okay, for example, write this equation. It states sodium reacts with chlorine to produce solid sodium chloride. Okay, so let's analyze what we're given here. Okay, it's telling us sodium. All right, so we know that. We know it's not sodium chloride with something else. It's sodium, which tells you is the element. And so that is Na, sodium. And we know that that is a solid. Okay, if you don't know, check that periodic table, or that table that we dealt with the physical states of the elements a few chapters back. So sodium is a solid. The keyword reacts tells you it's a plus sign. All right, so sodium reacts with chlorine. Now, they didn't say chlorine gas, they said chlorine. Key word is key suffix is INE, which tells you that's the element. Plus, it is one of the diatomic elements. So that is Cl2. Notice chlorine versus chloride. Chloride tells you that's ionic. All right, so chlorine is a gas. To produce is your keyword for the arrow, the reaction arrow. And then we got sodium chloride. Well, let's make sure we write the ions first. Okay, so we know that sodium metal is in the group 1 element will become a +1 ion. And chloride is a group 7 element, and it's a nonmetal, so it's going to gain an electron, so it will have a -1 charge. So we have equal charges, so we can put them together simply in a 1-to-1 ratio. So our formula for sodium chloride is NaCl, plus they're telling you the physical state, so it's a solid. Okay. Now, next thing we got to do is balance it. All right, so we got one sodium, one sodium. Sodiums are happy. The chlorines are not. I got 2 on the left, 1 on the right. So what if I put a 2 in front of sodium chloride? Okay, that's good. That balances my chlorines. I got 2 in the form of 2 chlorides and 2 chlorines. They're happy, but that kicks up my sodium. So I just simply put a 2 in front of sodium, the element sodium, and now I'm balanced. Okay. And what's fascinating about this reaction, this is sodium metal is very reactive, extremely reactive. It reacts violently with water. Okay. And doing so produces hydrogen gas and a lot of heat, which can ignite the hydrogen gas and gives you a nice little pop or explosion, depending on how much sodium you use. And then chlorine gas is a poison. Poisonous. So here you got a very active piece of metal that if you were to put that metal in your mouth, it would be a big problem. Or if you to inhale chlorine gas, that also would be a big problem. But when they're done reacting, you end up producing a product that you can put on your French fries, good old table salt, sodium chloride. And the only thing that happened here was a transfer of, well, actually 2 electrons. The 2 electrons in the sodium were transferred over to the chlorine to form the chloride, and 2 electrons are transferred to give us sodium chloride, something you can put on your French fries. The power of those electrons. Okay, so that's our analysis. First step, write the equation, balance it out. Oh, the physical state, excuse me. And then, of course, we're talking about it couldn't be sodium chloride, Cl2. Why? Because that would infer that sodium would be a +2 state. And we know it can't be because it's a group 1. So that formula would be totally incorrect. NaCl2. All right. Balance it out and then look at our ratio. It takes 2 sodium atoms to react with 1 molecule of chlorine gas to give us 2 molecules of sodium chloride. Okay. Here's another example again of taking a word sentence and converting that to a chemical reaction. All right. So we have aluminum, very similar to the previous one, reacts with bromine to produce solid aluminum bromide. So aluminum, good old Al, and we know that's a solid, reacts with, is our key for plus, bromine. Keyword bromine, INE, tells me that is the element, which is diatomic, which, can anybody know the physical state of bromine? It's a liquid. That is correct. Okay. And so we got a liquid bromine. Okay. To produce is the arrow, aluminum bromide. So we have solid aluminum bromide. We have an ionic compound. We got a metal and a non-metal combination. Let's first write the ions first. So we got aluminum that we know is part of the sweet 16. They have a constant oxidation state, which is a +3. It's in group 3. It's got 3 valence electrons. It wants to lose those because it's a metal. Okay. So you got a +3 state. Bromine, like chlorine, is in group 7. It will gain an electron with giving you a negative charge. Therefore, I need to have 3 bromides for every aluminum, and therefore our formula is AlBr3, and we're told the physical state, and that would be a solid. Okay. All right. So here we got to balance it. All right. So here we have 1 aluminum, 1 aluminum. Aluminum's happy. Bromine is not, because we got 3 on the right, 2 on the left. Okay. Well, look for a common number like the previous example we did. Okay. The common number here would be 6. So that tells me I need 3. If I put a 3 in front of bromine and put a 2 in front of aluminum bromide, now my BRs are balanced. I got 6 on both sides, but that kicks up my aluminum. No problem. Come over to the reactant side, put a 2 in front of aluminum. Now everybody's happy. Mother Nature is happy. 2 aluminums, 3 bromines to give us 2 aluminum bromides. Note the ratio here between reactants, the 2 to 3 ratio. Note it from bromine to aluminum bromide, it's a 3 to 2 ratio, or 2 to 3, whichever way you look at it. And from aluminum to aluminum bromide, It is a 2-to-2 ratio, or otherwise a 1-to-1, right? Because that ratio 2-to-2 divides into 1-to-1. 3 ratios. Another example of a combination reaction. All right, so now we write the reactions, okay? We have the states, and then we balance it like we just did. Okay. Basically, again, the coefficients, we add them until we got everything balanced. And if, like I said, if you write them, you can, at times, depending on how you do it, you can end up with this type of scenario. You can see 4, 6, and 4, it is balanced, but that's not the lowest terms because everything is divisible, in this case, by 2. Okay, so bringing those coefficients down to its lowest terms. All right, and be aware of the ratios because we'll be using those down the road. Okay, we got the reaction ratios, and that's just between aluminum and bromide, but the ratios also pertain to reactants and products. These two, this ratio I wrote here is just pertaining to the reactants, but they also pertain to reactants and products. All right, here's an interesting one. Write the reaction of phosphorus All right, I'm back. Something happened. Everybody with me still? All right. All right, we're good. All right, I'm back. I don't know what happened. I got kicked out and then came back in. All right, good old Cox. All right, so here we have this example. We have the reaction of phosphorus reacting with oxygen to make solids diphosphorus pentoxide. All right, here's a good example. We're making a covalent compound. The other ones we've been making were ionic compounds. All right, so let's break down the reaction to words. So the reaction of phosphorus, okay, so we know that's P, and that is S, it's a solid, reacting with, signals a plus, oxygen, we know is diatomic and a gas, okay? You make is our flag for the reaction arrow. So phosphorus plus oxygen reacting to make solid phosphorus diphosphorus pentoxide. So let's first write the parent elements, phosphorus and oxide, okay? And then we go back and check the prefixes. So di meaning 2 and pent meaning 5. Okay. And it's a solid. Diphosphorus pentoxide. All right. So you got the reaction. Now we got to balance it. All right. So what do? Well, there's a couple of ways to attack this. All right. You remember the previous example that we had 2 and 3 for, what was that, oxygen? We're looking for a common factor. Well, guess what? We have a 2 to 5 here. We could do the same thing, look for the common factor, which in this case would be what? What's the common factor between 2 and 5? What common number would that be? Exactly, 10. Okay, so if I put a 5 in front of oxygen, that gives me 10 oxygens. And if I put a 2 in front of diphosphorus pentoxide, I have 10 oxygens. So guess what? My oxygens are balanced now. And what that means is my phosphorus get upgraded, if you will, to 4. No problem. I come over here and put a 4 in front of phosphorus, and Mother Nature is happy. So now I got 4 phosphorus, do a double check. 4 phosphorus, 4 P's on the reactant side, 4 P's on the product side, 10 O's on the reactant side, and 10 O's on the product side. Everybody's happy. Look at my ratio, 4 to 5 as far as reactants are concerned. 4 to 5 ratio. Okay. From oxygen to product, it's a 5 to 2 ratio. Okay. And from phosphorus to the product, each one has a ratio. It's a 4 to 2 ratio. Okay. Or simply a 2 to 1, same thing. All right. So be aware of those ratios. We're going to use those a lot. So we write down the reactants like we did in the states. I went ahead and put them on as we went along, then we went and balanced it. In this case, I used a common factor, a number, which was 10 for the oxygens. All right. So another example this one's another example of a combination reaction, 2 elements reacting to form a compound. Here's a practice problem. Do this. I'll give the answer next. Well, I'll go ahead and give it to you. All right. Now here's a reaction. Before we do this, let's break it down. No. The last example, it did not stay. It did not stay. Diatomic oxygen was converted and now is in the form of diphosphorus pentoxide. Okay, it's not diatomic. It's only diatomic as a reactant. Okay, because now it's part of a compound. You see that, Claudia? Yeah. All right. Okay, here's one, which is another part of a type of reaction, but we'll give it a name when we get to it. But to predict this type of reaction, we use the solubility rules. But before we even do that, let's break it down. Let's write the reactants in their proper form, okay? And the proper formula, and let's see what we got. All right, so let's do that. All right, so the reaction is right in balance is this aqueous reaction where you have nickel 3 sulfate. Okay, nickel 3 sulfate. So let's do this. Let's first remember what the Roman numeral is, the charge for the oxidation state for nickel. So it's a +3 state. Then we have sulfate. Well, the keyword sulfate, not sulfide, IDE. The ATE should tell you. Let me go to the polyatomic ion table, the ATE or the ITE, right? And if you do that, you'll find it SO4 -2, okay, for nickel sulfate. Then it says plus, so that'll be a reaction. Now I'm going to write the ions first, and then we're going to write the combined formula to make sure we put it together correctly. Plus lead 2, which is Pb2 +2, and nitrate, which again, the H should send you to the polyatomic ion table, and you will see that it is NO3, okay? Produces is my keyword for my arrow, the reaction arrow. Produces nickel 3, we still have nickel 3, nitrate, NO3 minus, plus solid, they're telling you solid, lead plus 2, sulfate plus 2. So first step in all this is to write everything in ions. So therefore I can write the correct formula together. So nickel and sulfate, the very first one. Remember how I can put these together? I got to put them sufficiently so they cancel each other out. So I find a common number, right? And the common number is 6. So I need 2 nickel pluses and 3 sulfates. So that becomes Ni2 parentheses SO4 3. Okay?
Professor?
Yes.
Why you put 2?
2 where?
On the nickel.
Okay. Remember, I need a common number here. What's my common number between the 3 and the 2? Regardless of the chart.
Will be 6.
Yes. So I need 2 plus 3s to give me a total of plus 6, right?
Correct.
And I need 3 negative 2s to give me a total of negative 6. Right?
Right.
Okay, so that's why I need a 2 there, because I need 2 of the plus 3s to cancel out the 3 of the negative 2s. So that 2 becomes a subscript. So I need 2 nickels and 3 sulfates. See that?
That was the only one that I could not understand when I was watching the videos. I don't understand because if you put the 2 in front of the nickel, that means that this number 2 also go to the nickel and also go to sulfate, correct?
No. For when I put everything in ion form, this 2 is going to become the subscript. Only for the nickel, nothing to do with the sulfate. You follow what I'm saying? This 2 only tells me that I need 2 nickel atoms. So that's why I put a subscript 2. This 3 tells me I need 3 sulfate ions. Okay? The similar thing, let's do the next one. Maybe that will help. In the next one, I got lead 2 and nitrate. Well, in the nitrates, this is straightforward, right? You can see that I need 2 nitrates to balance out the plus 2 of the nickel. So that means that it's PB parentheses NO3 subscript and parentheses. Does that one make sense?
Yes.
Okay, now go over the arrow. Now we go over here. You can see that I have nickel 3, which is the same nickel 3 over there, but now it's combined with the nitrate. So I need 3 nitrates to balance the plus 3 of nickel. So that tells me this formula is NO3 parentheses there. Does that formula make sense?
Yes.
Okay, and then finally, the last one, both the lead and the sulfate have a plus 2 and a negative 2. So I simply need one of each. Oh, let me I don't need I just need one of each. So it's SO4. Now, furthermore, it tells me it's a solid. Okay. Now I'm in a water solution for these 2. The first 2 are aqueous. So it's AQ, and AQ for the nitrate. Okay. Now, if you go to the solubility rules, you will see that all the nitrates, everything with the nitrate is soluble. So it's AQ. Okay. But you will also see that lead sulfate is insoluble. So we got a solid. That's why it's an S. Okay. Now, it looks like the only one you had problems with was the first one, as far as,
Now I understood. Thank you.
okay, all right. Now, to balance these types of reactions, follow the polyatomic ions. Okay, what do I mean by that? Look what I have here. I have 3 sulfates over here, right? 3 sulfates. I only got 1 over here. So what if I put a 3 in front of my lead sulfate? Okay, that makes my sulfates balance. I got 3 over here, 3 in the 3 with lead sulfate. But then my lead increases to 3. Okay, so if I increase this to 3 here, what happens now? My lead is now balanced, but my nitrates get kicked up to 6. You see that here, 6? Okay, no problem. What if I put a 2 in front of my nickel nitrate? That gives me 6 nitrates, but my nickels now go up to 2, but no problem because by default, I already got 2 nickels. See how I balanced those? I just followed the polyatomic ions, the nitrates, the sulfates. I followed those and I balanced those, and the metals, the corresponding cations will balance by default. Does that make sense? So that's your hint for this type of reaction. This type, by the way, is called a double displacement reaction. Double displacement reaction. And this is only true, it's only true for this reaction to proceed if one of the products is insoluble. Notice the 2 reactants are soluble. In fact, if we were in the lab, we will have those 2 would be liquids that wouldn't be solids. It would be 2 clear solutions. The moment I put them together, it gets cloudy, it cloudies up. And that's because what's happening, the partners are exchanging. Think about it. I start off with nickel sulfate, I end up with nickel nitrate. I start off with lead nitrate, now I got lead sulfate. So the anions exchange partners with the cations. And then we look at the reactants and determine whether one of the reactants is soluble or not. If it's insoluble, we got a positive reaction. If both of the products are still soluble, then there's no reaction. Remember that. If both products are still soluble, no reaction. Only when one of them is insoluble that we get a positive reaction. Okay. So that's our reaction there after we balance it. And to balance it, follow the polyatomic ions for this type of reaction. Right, this table breaks down in general terms the types of reactions. We gave you some specific examples. Now we're going to give you all of the 6 reactions. The first one's called a combination reaction. You can see in general terms, you have A plus B 99.99 times. A and B are elements and they combine together like we did earlier with phosphorus and oxygen to form diphosphorus pentoxide. The product you form is a compound based on the 2 reactants. Okay, they combine together. The phosphorus and oxygen combine together to form, in this case, AB. A decomposition reaction is the opposite. Okay, another example of a combination reaction, I'm going to write them up here so you can see how I'm talking about. we did the example of hydrogen plus oxygen, which is another rocket fuel, actually. If you ever see a rocket take off, a big old flume of smoke. That smoke is mostly water vapor. This is the combination reaction. The two elements combine to form a compound. A decomposition reaction is the opposite, where you basically start off with a compound, and we can do the same thing to water. If I take water and I hit it with some electrical current, strong enough current, it will break up the hydrogen and the hydrogen and oxygen and water and break it back into the elements. That's why it's so important for us to find water out in space, because we're going to create oxygen, which we need to breathe, obviously, and we make hydrogen, which is a good fuel. Okay, so in here, decomposition, we're breaking it down. We're breaking a compound into its elements. Okay, combustion reaction. Okay, now what we have here is a general formula for CHCXHY. This is called a hydrocarbon. Hydrocarbon. Like I said, if you spent this past weekend barbecuing and using gas, you use propane. Propane is made up of nothing but carbon and hydrogen. If you happen to be a smoker and you got a lighter, you're flicking your bic, that is butane, also made up of nothing but carbon and hydrogen. So for Chem 130, when we talk about combustion reactions, we're talking about burning combustion of hydrocarbons only. And anytime you have a combustion reaction, anything to burn, what do you need, obviously? Oxygen, okay? Oxygen is a reactant. Without it, it would not burn. And for Chem 130, I emphasize the point. For Chem 130, there's only two products that you need to worry about when you have a combustion reaction. That is carbon dioxide and water, okay? I repeat that. For Chem 130, for a combustion reaction, which involves the burning or the combustion of a hydrocarbon, which is made up of nothing but carbon and hydrogen, you will only get two products, carbon dioxide and water. Obviously, in the real world, that's not the case, because when you combust a hydrocarbon in your vehicle, one of the gases coming out of your exhaust is carbon monoxide. And that's basically because of the inefficiency of our vehicles to efficiently burn oxygen. Okay. All right. So that's a combustion reaction. That's for number 4, acid-base reaction. We talked about this one. When you have, in the presence of an acid, anything that produces a proton, okay, and a base, that is anything that produces a hydroxide, a proton and hydroxide always gives us water, okay? Plus the corresponding salt, which depends, that is basically the cation of the base reacting with the anion of the acid to give us the corresponding ionic compound, which is some metal salt. Remember, a salt is not just sodium chloride. In chemistry, a salt, we're dealing with an ionic compound, which is basically a combination of a metal and a non-metal, okay? Now, a single replacement reaction. Let me clear this up a little bit. Look at the reaction here. What we have here is a metal reacting with an ionic compound. Okay, and what's happening if this reaction proceeds is the metals, the two metals, which is denoted here by M and A, the one metal displaces the other. So M displaces A to give us the new ionic compound MX. And then the A, which was an ion in the form of AX, now is an element. It gets converted back to an element. Classic example of this, so you're familiar with this, is plating. You know, you have gold plating, you have copper plating, you have plating, chrome, you have plating of all kinds of different metals. Okay. And that's what generally happens in that plating. You have the metal that you want to be plated back onto your whatever you want to plate. It starts off in the ionic form and then gets converted back to the elemental form. So you can have gold, which is in the ion form, and now back plated gold, which is actual gold, but it's been plated on some substrate. Okay. Now, for this reaction to go as written, we have to rely on the activity series on the periodic table. That is right above the solubility table on the periodic table. There's a little table in between there. Check that out. We're going to use that, okay, to determine whether a reaction. Now, in that case, it's very simple with respect to you ask a couple of questions and that's it. And that determines whether the reaction proceeds or not, okay? All right, and finally, the last one is just like that example we just went through with the nickel and the lead, okay? We call that a double displacement reaction. Notice we have two different reactants. We got M1 and M2, which those aren't how many atoms. M1 and M2 just telling you they're two different metals, okay? The subscripts here are not telling you how many numbers. I repeat that. The subscript here, the 1 and 2, tell you they're two different metals. And then X and Y are two different, most of the time, 99.9% of the time, they are the polyatomic ions. And what's happening here is the partners are exchanging, they're just changing position. The M1 now combines with the Y to form the M1Y. And the other combination, obviously, is the M2 combines with the X. It gives us a new species, the M2X. Now, if M1, you use the solubility rules. If M1 is soluble, first of all, everybody is an aqueous solution, okay, both the reactants. If M1Y is soluble, then it is aqueous. If M2X is insoluble, and then it's solid, and then plus it means we have a reaction. That means one of the new products has to be insoluble for this reaction to occur, like the previous example we just did. Remember that one of the products was insoluble. That one, remember this one, and we have lead sulfate. And this is an example of a double displacement reaction, okay? So there you go. All the chemical reactions that occur out there boils down to 6 different types, okay? And here's some examples. We have phosphorus and oxygen. In this case, it reacts to form diphosphorus tetroxide. It's a combination reaction. You can see that I have 2 elements reacting to form 1 compound. Then we do a balancing. You got to make sure you're balanced. So it requires 2 phosphorus, 2 oxygens to give us 1 product. Okay. Decomposition reaction. In this example, we have iron 3 oxide. Iron 3 oxide reacts such that it breaks apart. The iron and the oxygen go back to elemental form to create iron and oxygen. So basically, this is rust. Iron 3 oxide, aka rust, under heat conditions and some other factors, you can regenerate the iron and generate oxygen. Okay, and yeah, this is balanced. Okay, combustion reaction. In this case, that is the formula for propane. So this weekend when you were barbecuing something, you were burning C3H8. Okay, propane. Down here in the bottom left is the basically the formula, the structure. The black indicates the carbon and the white indicates the hydrogen. All right, now to balance these equations, you have a series of steps for you. This is a combustion reaction only. Step number one, balance the carbons first. Okay. And so we got here the C3H8 plus oxygen gives us carbon dioxide and water. So we can balance the carbons first. I put a 3 in front of carbon dioxide to balance the carbons. Number 2, balance the hydrogens next. Okay. So I got 8 over here in the form of propane, but I only got 2 in the form of water. So what if I put a 4 in front of water? That balances my hydrogens. I'm good to go with carbon. I'm good to go with hydrogen. And then finally, number 3, balance the oxygens. Okay. I have 2 O's over here. I have 6 O's in the form of carbon dioxide and 4 oxygens in the form of water. So that gives me a total of 10 oxygens. Okay. 10 oxygens total, 6 in the form of carbon dioxide, 6 in the form of water. So to balance my oxygens, I just need to add a 5 in front of O2. That gives me a total of 10 oxygen. So I have balanced my combustion reaction. Carbon first, hydrogen next, and then finally oxygen. Okay, and there you go. Combustion reaction. This is telling you the same thing. Do oxygen, carbon, hydrogen, then oxygens. Okay. Remember, for combustion reactions, you should know the only 2 products and the reactant required for any hydrocarbon. Oxygen is necessary. You all know that. Again, for anything to burn here, you need oxygen. And then the only 2 products you obtain will be carbon dioxide and water. And then to balance them, you follow the format: carbon first, then hydrogen, then finally the oxygens. Okay. Acid-base reactions. Remember, it's the acid plus a base gives you water. Always, you know the product and then the corresponding salt. Now, to balance these, to balance acid-base reactions, remember I said earlier with the double displacement reactions, follow the polyatomic ions. Here, follow the hydroxide and the protons, and everything else will fall in place. For example, we have hydrochloric acid, HCl, reacting with barium hydroxide, okay? Now, what do we know? We know that it's a 1-to-1. So from every proton that you have, you need 1 hydroxide, and that will always give you 1 water, okay? We got 2 hydroxides here. So what does that tell you? That tells you that I need 2 protons. Well, I need to put a 2 in front of HCl. I also know that I'm going to make water, right? But since I started with 2 hydroxides, I needed 2 protons. How many waters am I going to make? I'm going to make 2. Why? Because it's a 1-to-1. If I start 2 here, 2 here, I get 2 waters. If I started with 1,000,000 protons and 1,000,000 hydroxides, I'm going to get 1,000,000 waters, okay? So I got 2 protons, 2 hydroxides gives me 2 waters. Now I just need the salts, and that's going to be the anion of my acid and the cation of my base. So before I put them together, I first write them out as ions. I know that barium ion is a +2. How do I know that? Well, two reasons. One, I got 2 hydroxides in the structure. I know that, or should know that, the hydroxides each are -1, right? As far as their charge. And since I got 2 of them, that implies barium is a +2. If I didn't know that, what else do I know about barium? It's in group 2A. That means it's in group 2A, which means you got 2 valence electrons, and it's a metal, which means it's going to lose those 2 valence electrons, which will give you a +2 charge. All right. The chlorides are in group 7, and all the halides, bromine, fluorine, chlorine, bromine, iodine, are going to have a negative charge when they become the chloride. That tells me I need 2 chlorides for every barium ion. So now I can write BaCl2. Okay, BaCl2. Now, you know what? In this scenario, the bariums and the chlorides cancel, are balanced automatically just by default. 1 barium, 1 barium. 2 chlorides, 2 chlorides. 4 hydrogens. Well, I got 2 in the form of HCl and 2 in the form of hydroxide. So my hydrogens are balanced and my oxygens are balanced. Okay, so by following the proton and the hydroxides, I automatically balance this reaction. And I don't forget the states. Obviously, water is a liquid, and barium chloride, if we look up barium chloride, you'll find it. Let me turn this up. To be soluble. If you look that up in the solubility rules, the chlorides of barium are soluble, hence we use AQ. All right, let's analyze the next one. We have, if you don't recognize the formula, recognize that we have hydrogen written first. That's a good indication that 99 times out of 10 that you have an acid. Okay, so you may go look through your notes and say, oh, all right. I recognize PO4 as the phosphate. Remember the phosphate polyatomic ion? When I put the hydrogens back in there, I make phosphoric acid. Okay, just like Cl, I got Cl, the chloride. If I put hydrogen back in the chloride, I make hydrochloric acid if it's an aqueous system. So I got phosphoric acid here. Then I use calcium hydroxide, AKA Tums. Okay, it's a base. Now, as I stated before, follow protons and follow the hydroxides. I have 2 over here, 2 hydroxides and 3 protons. Remember, these guys are going to dissociate in water to give you 3 protons. So I need them to react with each other such that they cancel each other out. It's a neutralization reaction. So that tells me that I need a common number. I got a 2 and a 3. Common number again would be 6. So if I put a 2 in front of phosphoric acid, that would give me 6 protons. And if I put a 3 in front of calcium hydroxide, guess what? That gives me a total of 6. So now I got 6 protons coming here and 6 hydroxides from the calcium hydroxide. And guess what? How many waters am I going to make with that? I'm going to make 6 waters. Okay, because these 6 protons will combine with the 6 hydroxides to give me 6 waters. Now I look at the corresponding salt, which is the calcium and the phosphate. I first put them together in ionic form. The calcium is a +2, and the phosphate is a -2, -3, excuse me. Okay, so again, I have a dissimilar charge, so I need a common factor, and this would be 6 again. So I need 3 calcium and 2 phosphates. So my formula becomes calcium 3, PO4, remember the parentheses. We want to add more than 1 phosphate, so we could give it a parenthesis. So our formula becomes Ca3, parentheses, PO4, 2. Okay. So acid-base reactions, I emphasize, follow the protons. We did that up here, follow the hydroxides. Okay. It would tell us how many waters we have. Then the corresponding salts, they're going to come together. First, write them in ionic form first before you put them together, to make sure you put them together in that correct ratio. The more you do these, the more examples you do, it gets to the point where you don't have to put them in ionic form. You already recognize them. But for right now, put them in ionic form, and then it will tell you how many of each you need together to be together to write the actual formula at the end. Okay. All right. So let me clear this up a little bit. Okay, 3 and 3, what we just talked about. And if you do, I forgot to put the physical state of calcium phosphate. If you look up the phosphates on the solubility table, you'll see that this phosphate is insoluble. Hence, solid. Okay. Which brings us to the single replacement reaction. Now, to utilize this, and here's a general reaction. We got some metal reacting with some ionic compound, which is a different metal, which is designated as the letter A here. And if this reaction proceeds, the metals replace each other, so that the A, which was an ionic form, now is an elemental form. Okay, just like plating. Now, in order for this to happen, the metal that is an elemental form has to be more reactive than the metal that's in ionic form. And we utilize what's called the activity series. Okay. On your periodic table, you'll find this listing here, which is called the activity series. Is right above the solubility rules. And you can see here that lithium is listed first, and then at the other end, at the end of this table is Au, which is the gold. Oh, I tell you what, let's do a quick 10-minute break here, if you don't mind. It's 10:26. How about we come back at 2:36? Okay. Let's do that, and I will temporarily pause everything. Okay, guys, thank you. I needed to do something real quick. All right, so the activity series. Just to refresh your memory, let me pull up the periodic table. And on the periodic table, like I stated, right above the solubility rules, there's a little table listed there as the activity series and list of active metals. Okay, so how this works is as follows. The way it's listed, lithium is the most reactive metal there is, with gold, Au, being the least reactive metal. Okay. Now, the ones that are highlighted in your periodic table, they're highlighted by they're bold or underlined. Here, they're highlighted in white. So lithium through sodium, those guys are extremely reactive. In fact, just by in the presence of water, they react violently. That's why those are highlighted that way. The other metal, from magnesium all the way up to lead, they will react. However, they require a little bit more strength as far as their environment. They will have to react with an acid, an aqueous solution like hydrochloric acid, but they will react under those conditions. And then above copper and silver and gold, it takes some fairly vigorous conditions to get those to react. Now, this is a relative scale. And it being relative, that means it is relative to hydrogen, which is right here. Okay, so the elemental form of hydrogen obviously is H2, or the salt form, I'll explain that in a minute, of hydrogen will be either in the form of water, H2O, or H2. Salt form, H2O, elemental form, H. Okay. And so what they did is do a series of experiments relative to hydrogen, to water, and hydrogen is the reference point. You would think that's kind of different because hydrogen is not a metal. Nevertheless, this scale is based on hydrogen. All right. The way it works is this: is the most reactive metal wants to be in ionic form. So, for example, if we look at, say, calcium and magnesium, potassium, what am I saying? Potassium is much more reactive than magnesium. And if you're looking at a reaction, let's say between potassium plus, let's say, magnesium chloride, the question is, will this reaction proceed? So what you do first, step number one, is you determine which metal is more reactive, regardless if it's in elemental form or ionic form. So here we're comparing potassium versus magnesium. We go to the activity series. Activity series tells us potassium is a lot more reactive than magnesium. Okay, that's good. Second question, is potassium in ionic form? Okay, based on the reaction. If the answer is no, then you have a reaction. Okay, so you go to this example. Is potassium in ionic form? And the answer is no. Why? It's an elemental form. Therefore, reaction proceeds and the metals exchange position. Okay. If the answer is yes, then you get no reaction. If this was, say, magnesium plus potassium chloride, well, potassium is most reactive and it is in ionic form already, so no reaction will proceed. Okay. So if the most reactive metal is in ionic form, no reaction. If it's not in ionic form, a reaction proceeds and you simply switch and rotate exchange the metals. Let me clear this and we'll do some examples. Okay. And this is basically everything I just explained here for your reading pleasure. After you do that, obviously we're going to balance the equation. Let's take a look at this reaction here. We have here zinc nitrate plus sodium. Okay, question number one. We are comparing the metals. So number one, which is more reactive? Zinc versus sodium. Well, we look at the activity series, we isolate sodium and we isolate zinc, and we find out that sodium is more reactive than zinc. Okay. Question number two, is sodium is the most reactive in ionic form? Okay. Answer is no. Therefore, we get a reaction. okay? And what we're doing is we are just exchanging the partners. So zinc ion becomes zinc metal, and sodium element becomes ionic sodium. So that's what we're going to do here is we're making zinc solid, okay? And then we're going to replace sodium, but before we do that, we got to write that in ionic form, just like we were doing in the previous equations. We know that sodium has a +1, and we're dealing with nitrate, okay? Nitrates have a -1, okay? So therefore, the formula for sodium nitrate would be, let's write it over here. Here's the arrow. It will be zinc solid plus sodium nitrate would be our formula. We have displaced the zinc with the metal sodium, because sodium is more reactive. It wants to be in ionic form, much more so than zinc. Once we do that, now it's a matter of balancing it. Let me clear this up a little bit. We'll bring the other way, write it out. Okay, we see how we exchange the partners here. We know that zinc, as far as the physical state, is a solid. We know from the solubility rules that sodium nitrate is aqueous. Okay, remember that anything attached or partnered with sodium, the big four, one of the big four is soluble. So that would be aqueous. Okay. We balance it. Here we balance it. We have polyatomic ions. Follow the polyatomic ions to balance them. We have zinc nitrate with 2 nitrates. So we simply put a 2 in front of sodium nitrate, and everything balances out. That increases our sodium, which we're going to put a 2 there, a 2 in front of sodium. And we're, by default, everything else balances out. Okay. What does that mean? That means that this reaction, I go backwards. Okay. If we go with, for example, using this reaction, if you were asked, well, sodium nitrate plus zinc, would this reaction proceed? Well, same scenario. Compare the two metals. Sodium is much more reactive than zinc. That hasn't changed. Second question is the most reactive metal in ionic form? And the answer is yes, it's already in sodium nitrate. So what we end up with is no reaction. And this, if you do the reverse, go the reverse direction. So this is a one-way reaction. So if you get one reaction that tells you no reaction, well, guess what? The opposite reaction will be positive, okay? All right, so let's do a couple more. I'm trying to, of course, not sodium nitrate would not be, that formula would be incorrect for sodium nitrate because we know sodium is a +1. The nitrates are a -1. That would infer that sodium would be a +2, and it can't be because sodium is in group 1A, only one valence electron, okay? All right, so follow the nitrates. You can see how you can balance it out. Let's work this one through. Okay, we got strontium bromide and aluminum. Well, we got to find them. We got to find aluminum. There's aluminum. All right, and strontium right there. So strontium is much more reactive. Number one. SR is more reactive than aluminum, okay? Second question, is the most reactive metal in ionic form? Answer is yes. That means no reaction. Why? Because the most reactive metal is already in ionic form. So no reaction. But the opposite reaction would work. In fact, aluminum bromide plus strontium would, yes, there'll be a reaction. because strontium is the most reactive metal and it's not in ionic form. So the reaction will proceed to give you strontium bromide and aluminum metal. Okay. All right. HCl versus aluminum. Well, if you look at this, the activity series, Al is a lot more reactive than hydrogen. Yeah, aluminum versus hydrogen. And remember that the hydrogen, its ionic form can be either its molecular form, elemental form is H2 or H plus, or it could be in the form of water. Okay. And over here, H, hydrogen, is in the form of the proton, H plus, right? This is an acid. And like I said earlier, the other aspect I explained was when you look at the metals, starting with magnesium and going all the way up to lead, these guys in here, in order for them to react, they need something a lot stronger than just water. The first ones that were highlighted in white and underscored, you simply put them in water and extremely reactive. But the other guys up to hydrogen require a strong acid. And we can go through the same scenario asking the question. Here in this case, aluminum is a lot more reactive than hydrogen. Aluminum is not an elemental form, so therefore aluminum will exchange places with the hydrogen, okay? And the hydrogen will go back to elemental form, which is H2. Okay, because aluminum is more reactive than hydrogen. Okay, which means that aluminum will form, we're going to form H2 gas, because this hydrogen goes back from the ionic form back to elemental form, which is hydrogen, and then we're going to make aluminum. Well, before we put them together, we need to make sure we put them together properly. And as we've done before, we first write the ionic form of aluminum, and we can see it's a +3. That means we need 3 chlorides, okay, to give us aluminum chloride. Okay, and then now we do the balancing. All right, so let me draw it out and clear this up a little bit. There we go. And there's our balanced chemical reaction. Yeah, watch Dr. Kim's videos, plus obviously the one we were talking about here once I uploaded, to listen to her version of this particular chapter, give you more resources. Okay. To summarize this with respect to single replacement reactions, is you, like I stated, you first determine the most reactive metal. Unless it is hydrogen, HCl, then we're talking about metal versus hydrogen gas. Okay. If the most reactive metal is already in salt form, then there's no reaction. If it's not in salt form, then there is a reaction. Okay. Process. Double displacement reaction. We did an example of this. Okay. This is governed by the solubility rules. Solubility rules, to refresh your memory, are right down the bottom, right below activity series. So refresh your memory on the solubility rules. And again, we are looking at the products. If one of the products is insoluble based on the solubility rules, then a reaction proceeded. Is displacement reaction? It's a good question. I've always known it as a displacement reaction, and that's what it's called. But in reality, if you think about it, yes, it is replacing it. You are replacing one metal for the other. So, you know, it's either tomato, you think about it, but it is called a displacement reaction. If you look in the textbooks, they won't refer to it as a replacement reaction. All right. Pause for a precipitation reaction for it to proceed. If both products, here's the key thing, if both new products that you make are insoluble, soluble, and no reaction is proceeded. All you've done is exchange partners. Nothing happened, nothing precipitated. And remember, all you're doing in double replacement reactions, you are just changing the cation and the anion. The A is now going to partner up with the Y, and let me change the color here. And the X now is going to be partner up with the B. And then we look at the solubility rules to see which one of these is soluble or insoluble. And if one of them is insoluble, then the reaction proceeds. Okay. That soluble is a solid, it's called a precipitate. And we use that quite often. If you were looking for chlorides in your water, you normally treat it with a small sample of your water with silver nitrate. Silver nitrate will create a new partner, silver chloride. We know from the solubility rules that silver chlorides are insoluble. And so that will be a test for at least chlorides in your water if you get a precipitate. All right. No reaction if all of them are if all the products, the new products are both soluble. Okay, and it deals with, as I stated, I can emphasize it, is the solubility rules. Refresh your memory on this, and that's how you determine whether a reaction proceeds or not. For example, you can very quickly compare and look at the new partners and, you know, write them out. Here we have barium. Now going to partner up with sulfate. Excuse me, I can do that correctly. With the sulfate. And then let me change the color a little bit. And then we're going to have magnesium repartnering with this nitrate. So what I'm going to do first is write the ions of the product. So I got barium. So let's assume that's the arrow here. So I got barium, which you know is in group 2. Okay, so you're going to get a +2. If you didn't know that, if you look at the starting materials, barium nitrate, nitrates all have a -1. There's 2 of them that infers barium must be a +2, right? And we know that sulfates are a -2. Okay, and then you know what I should have done? Let me do this. Let me put everything in color there just to make sure. So we got the red here, we got the barium, as stated, was a +2, and the sulfates are a -2. All right, so I can put these together as a 1-to-1. So I got barium sulfate. Okay. Now the other one is magnesium, which we know is in +2. 2A group 2A, so it's kind of a +2 ionic form. We also know that because it's attached to sulfates, which have a -2. And then the nitrates each have a -1. So we're going to need 2 of these. So that means that we're going to have magnesium nitrate. It will be our formula. Okay. Once we figure out the formulas of the new products, okay, we quickly check the solubility rules. Well, if we look at nitrates, that is number 3. Nitrates are soluble regardless of whom they are bonded with. All nitrates are soluble. So this one is soluble. The sulfates, we look up the sulfates, is number 5 here. All sulfates are soluble with the exception of those, 5 of them. One of them happens to be barium sulfate, which are insoluble. Therefore, barium sulfate there is a solid. Therefore, we've got a reaction. And now we simply, by default, if you look at it, you'll see that we are balanced all by default. Follow the nitrates, the polyatomic ions, I should say. We got 2 nitrates in the product side, 2 in the reactant side, 2 and 2. Sulfate, 1 sulfate, 1 sulfate, and 1 of each metal. So just by default, this particular reaction just defaulted, balanced all by itself. Okay. All right. So that's what we're doing with double displacement reactions. Remember, you follow the polyatomic ions. I hope you balance them out. Here we got this one. Let's do the same analysis here. Okay. The partners we're going to get is lead and iodine. And that's a good flag to tell you I'm going to get a precipitate here when you're dealing with the heavy metals. Because we know already for number 3 that all nitrates are soluble, regardless of who the cation is. But the fact that you got lead in here and it's going to partner with something else, that's a good indication you're probably going to have a precipitate. And then our new combination will be potassium and the nitrates. So let's write out the new product. So I got lead. Now, the question is, which lead are we talking about? Because it's not part of 16. We know that each nitrate has a -1, so we get a total of -2 for the nitrates. That implies that this lead must be lead 2. So we got lead 2 combining with iodide, okay? That means that we're going to need 2 iodides for every lead. So that gives us the formula of PbI2. We'll come back to the solubility, but we can look that up real quick. Halogens, number 4, normally are soluble with the exception of the silver, mercury, and lead. So this tells us right away we got a precipitate. Now let's quickly do the other, which is potassium, which is a +1, and the nitrates, which are, we know, are -1. And so their formula will be potassium nitrate, KNO3. Okay. I can put a 2 in front, just follow the polyatomic ions, nitrates, okay? I got 2 there, and I can put a 2 in front of potassium iodide, and I think everything balances out. Follow the nitrates. I got 2 nitrates in potassium nitrate. I got 2 already in lead nitrate, so they're balanced. Then I got to put a 2 in front of Ki to give us 2 potassium, balance of the potassium, and then that gives me 2 iodides, but they balance out already because of the formula necessary for lead iodide. 2 iodide. Now let's clear it up here and we'll put it right there. There you go. Okay. Finally here, I don't think we can do it as much, but new partner would be barium nitrate and silver chloride, a good heavy metal silver. We know already all nitrates are soluble, number 3, okay? But we got silver up front, recombining with the chloride. So that's number 4. The halides normally are soluble, soluble with the exception of silver, mercury, and lead. So the new partner, silver chloride, would definitely be insoluble, okay? And so we have a reaction. And That's our balanced chemical equation. So it's a positive reaction because silver chloride is insoluble. Okay. Which brings us to what are called redox reactions. Well, many of the reactions that we just talked about, single replacement, combination reaction, decomposition, are also called redox. Now, what we mean by redox is a combination of the terms reduction and oxidation. That means in this reaction that some metal or something underwent reduction and something underwent oxidation. Now, to refresh your memory, oxidation is the loss of electrons. Reduction is the gain of electrons. And so they occur simultaneously. You can't have one or the other. When you have reduction occurring someplace, oxidation is occurring someplace else. If you're running on your battery right now or your electronic device, you are undergoing a redox reaction to create electrons, which then power your electronic device, okay? And many of these reactions we dealt with can be classified in a general broad sense and call them redox reactions. They're not specific names, but they're only called redox reactions because they undergo oxidation and reduction simultaneously, right? So basically reduction, the element's charge goes down. Why? Because they gain electrons, which are negative. And oxidation is when the element's charge or oxidation number goes up because it lost electrons, okay? You can't have one without the other, occur simultaneously. All right, we know elements in the natural state, all the elements have a zero state because they have an equal number of protons and equal number of electrons. It is when they lose or gain these electrons that now we have a net charge, either positive or negative, depending on what they did, okay? So we know, it's a refresher, we know about this, all the metals through group 1 through 3 have a positive 1 through 3 because of lost electrons. Group 4 can vary from a -4 to a +4 in any combination within. And then at that point, group 5 forward, they start gaining electrons. We end up with a -3, -2, and -1. Okay. And then obviously group 8, because the octet is fulfilled, it's at a charge oxidation state of 0. Remember, for these charges to occur from the neutral state, the driving force is that octet. By losing electrons, now the new orbital, the new valence shell has 8 electrons around it. So it's stable, much more stable. By gaining electrons, you have now fulfilled the octet rule, adding more electrons into your orbits, okay? All right, so losing the electrons means that the charge goes up. For example, you see copper has a 0 charge because it is the element. And so we could, it's a zero charge. It's neutral, but it's a metal. In this case, it can lose 2 electrons or 1, but in this case, it lost 2 electrons. So one product is 2 electrons. So solid copper is oxidized here, okay? Oh, let me back it up. Solid copper is oxidized because its oxidation number state went up. So what is oxidized is also called the reducing agent. It is the agent because it offers electrons for some other moiety to gain those electrons for it to be reduced. So hence it is called the reducing agent, okay? What is oxidized is the reducing agent. Now, in this example, sulfur is gaining electrons to become sulfide. It's a nonmetal. It will gain 2 electrons because it's in group 6. 6A has 6 valence electrons. It has room for 2 more electrons, and it will pick those up. to fulfill the octet. When the octet is full, it becomes sulfide. So in this case, sulfur is reduced because its oxidation number has dropped in value numerically. It now becomes a -2. 0 is our neutral point. If you lose electrons, your number goes up. So that value goes up in magnitude. Remember, negative numbers are less than 0. So their value of number decreases. So what is reduced is called the oxidizing agent. Okay. All right. Can't have one without the other. So that's always occurring simultaneously. Okay. So when you answer the question is, we're talking about what is oxidized? It's that whole compound, not just one specific part of it. For example, we'll do an example here. We have the copper ion, okay, reacting with iron, and there's an exchange here. Excuse me. Where copper now goes from a +2 state to a 0 state. Okay, so it got reduced because it picked up 2 electrons, 2 negative electrons. Iron, on the other hand, went from a 0 state, a neutral state, and it lost 2 electrons to go to the iron 2 state. Okay, so it underwent oxidation. It got oxidized. Okay? And this occurred simultaneously. So iron gives up the electrons, copper ion picks them up. Okay, because the iron is a lot more reactive than the copper. And that's why iron wants to be more in the ionic state than copper does. All right, so what is reduced is the iron metal, the solid, and excuse me, what is oxidized? What is reduced is the copper ion, which makes the copper ion +2 the oxidizing agent, and the iron is the reducing agent. Okay. All right. Here's another an example. We have a species. This is a chemical used in cancer treatment, platinum copper, platinum-based material. We have cobalt-3 nitrate. Okay. Now, how do I know that's cobalt-3? Because I know that the nitrates each are a -1, and there's 3 of them. Okay. There's 3 of them. And so that becomes cobalt-3 nitrate. Then we got, in the presence of platinum, it will react to form platinum-3 nitrate and cobalt metal. Okay. So this goes from a +3 state to a 0 state. So that means it was reduced and underwent reduction. Platinum goes from a 0 state, a neutral state, because that is the element, and undergoes reaction and picks up those, gives up those 3 electrons, I should say, to undergo to a +3 state. It underwent oxidation, went from 0 to +3. It does that by losing 3 electrons. Okay, so what is oxidized is the platinum. What is reduced is the whole compound here, in this case, cobalt nitrate, cobalt-3 nitrate. And that makes it the oxidizing agent. Cobalt-3 nitrate is the oxidizing agent, right? And platinum is the reducing agent. All right, so that's the name there, cobalt-3 nitrate. I know that because the nitrates each are -1, right? Go through your polyatomic table. Nitrate, -1. There's 3 of them, and that infers that cobalt must be in the +3 state. hence the Roman numeral 3. Okay, do check the other videos. There are other videos concerning this topic, Dr. Tim. Yeah, the more references, the more resources you have, the better, hopefully a better understanding you get of this. But all right, to summarize this particular chapter, be familiar with the solubility rules and how to use it and how to use the activity series, okay? Be able to recognize and balance a combustion reaction. A combustion reaction, first of all, for Chem 130 consists of a hydrocarbon, okay? Let me write this down. For a combustion reaction will be a hydrocarbon, which is always will be something made up of nothing but carbon and hydrogen. In fact, the smallest X value there is 1 carbon, and the smallest Y value there is 4 carbons. That's methane. Okay. And anytime there is a combustion reaction, you always need oxygen. Okay. Oxygen is necessary for anything to burn. Now for Chem 130, the only 2 products you get for a combustion reaction will be water plus carbon dioxide. That's why it's important that you kind of minimize the CO2 emissions, because those CO2s go up into the atmosphere and act as a blanket up in the upper atmosphere, and actually cause the heat that is absorbed by the sun that normally would go out to space but get reflected back to Earth. Kind of acts like, very similar to your vehicle on a hot summer day, in the morning. You take off someplace, you get the air conditioner running, you get to where you got to go, car's nice and cool inside. You come back after 4 hours, you park someplace, you maybe go to class, you come back 4 hours later, it's 100+ degrees outside, you open that door up, pretty hot in there, right? Yeah, and that's what's happening with excess gases that get up there in the atmosphere. They're acting as a blanket, a reflective blanket, and it's causing heat that normally would go out to space to come back in to trapped, causing all kinds of problems. So anyway, combustion reaction, hydrocarbon, oxygen, products, water, and carbon dioxide. Okay, decomposition reaction. That's basically, oh yeah, well, let me restate this. I was talking combustion and I meant to say combination. I apologize. I'll come back to it. Combination reaction. Let me restart again. I had combustion in my head here. Combination reaction, normally coming together of 2 elements, A plus B, to give us AB, some compound, okay? Decomposition reaction. Taking a compound like AB and doing something to it to break it back to the elements, A plus B. Okay. Single replacement reactions. We use the activity series to predict this. Generally, we got a metal, some metal M, plus some metal, which I'll designate as AX. And depending on the reactivity of the 2 metals, M and X, there's going to be an exchange to create MX plus A. Okay. If the most reactive metal is not in ionic form, then reaction proceeds to form MX if M is more reactive. If A is more reactive, then there's no reaction because it's already in ionic form. Okay. Double replacement reaction generally means that we have, let's say, My plus AX, there's an exchange of partners. So now we have MX plus AY. Okay. Now, depending on the solubility of the products, if MX is insoluble, then we get a reaction. In fact, if any of the products are insoluble, we get a positive reaction. And if any of the products are insoluble, there's no reaction occurring. Okay. Acid-base reaction. That is the combination of an acid and a proton, in which I'll have to write H plus the proton plus the hydroxide reacts to give us H2O. Acid-base reaction or neutralization reaction. Okay. And then finally, the combustion reaction, which I was talking about, jumped way ahead, where I have a hydrocarbon, which is nothing more but a species that is made up of nothing but carbon and hydrogen. I haven't counted.
Sorry, I don't have any information about that, but I found something related. Do you want to know what wiped out most of the Native
Whoa.
Americans?
Sorry about that. My Google kicked off. I don't know, misunderstood me. Must have heard me, thought I was asking it something. Yeah. Just shut it off. Hold that 1 second. Let me shut off Google. It's hooked up to my speaker, phone speaker, so it thought I was talking to it. All right, let's go back. Combustion reaction. Made up, let me write it up here. Carbon and hydrogen only reacting with water, excuse me, oxygen. I'm having a rough day today here. To give us only water plus carbon dioxide for CAM 130, okay? To balance those, remember, balance the carbon first, the hydrogen, then the oxygen, okay? To acid-base reactions, to balance those, follow the protons and the hydroxide. The single replacement and the double replacement, sometimes those are pretty straightforward. Those are a lot of those are with the single replacement, you can do the trial and error. The double replacement, most of those deal with polyatomic ions, follow the polyatomic ions, okay? And acid base, I already told you that, protons and hydroxides. All right, so be able to identify what is being oxidized, what is reduced, and their corresponding agent, whether it's an oxidizing agent or reduction agent. Other than that, ladies and gentlemen, congratulations. 6 more chapters to go. And we'll do 2 of them on Thursday because they're very short. Okay. All right. Let me stop the share.